record on this computer. Okay. And right, so let me share here my screen. Share. All right. So this is the example we're going to do. Again, you didn't see any equation, right, or anything like that. That's because there is no specific type of equation. It's basically volume balance, mass balance calculation that you will learn it through this example. Okay. So the example might seem a bit complex at the first sight, but we'll go over it, we'll talk about it, and we'll solve it together. Okay. All right, so you can download it if you want in front of you, but it's also here on the screen. So we have a casing which have an outside diameter of 3 and 3/8 inch. That is 13 3/8 inch. That is basically 13.375 inches, and an inside diameter of 12.415 inches, right? So that's the inner outer diameter, and it's to be cemented at a depth of 2,500 feet. Okay, so what does that mean? That means that the length of your casing is 2,500 feet from the surface all the way to the bottom. Okay, that seems to be a surface casing, right? Which is basically kind of on that range of depths. Now you have a 40 feet shoe joint will be used between the float collar and the guide shoe. Okay, so what does it mean? So usually when you run your casing, let me open another screen. All right. So when you run your casing, usually you have basically a couple of things here, right? If you go back there, it says that there is a 40 feet shoe joint will be used between the float collar and the guide shoe. Okay, what is float collar? Float collar is basically, let's say this is your well bore, right? And you want to run your casing. This is your casing run all the way to the 2,500 feet. And usually you don't basically drill up to that depth. You have drilled slightly more. So this is your well bore, which is continued, right? And this is where your casing will be set, right? Well, float collar is basically something that it's a one-way check valve. You probably remember from, again, axial tension calculations that in one of those homework problems, part 3, we had a float collar at the bottom. It was basically, we discussed it. It was basically a check valve, right? So it's a check valve that basically sits here at the bottom of the casing, right? It's a one-way valve. So it only allows the fluid to pass it this direction and not the other way around, okay? Now, when you send the casing to the bottom of the well bore, you usually attach something else to it, and that is called guide shoe. So if you go back here, there is a 40 feet guide shoe, okay? And the guide shoe is a heavy, basically, what did I do? The guide shoe is a 40 feet piece of basically pipe, which is heavy, okay? So let's say this is your guide shoe. And this guide shoe basically usually at the bottom have some other shapes. If you look at basically the slides later on, you will see that. But there is a hole inside this guide shoe here, okay? There is a hole here, and the rest is basically solid steel. And the reason that we use this is basically we want to allow basically the casing to be guided through the wellbore from the surface all the way to the bottom. Okay, so that's the reason that we want to have that. We want it to be centralized, so there are centralizers, but this heavy weight that is basically at the bottom will help us to guide the casing all the way to the bottom of the wellbore. Okay, so this length, which is here from the, let me double check the numbers here. So you have basically 40 feet shoe joint will be used between the float collar and the guide shoe. Okay, so basically you have a, I think there is a space here, let me double check that, but there is a, it's not, you know, completely here connected as I draw it. It's basically there is a 40 feet per problem distance here, and then you have that basically heavy piece of metal, right, at the bottom. So what you want to do based on this problem is this distance is given to you, right, 40 feet, right? Also, the length from the surface all the way to this point is given to you to be 2,500 feet. It's very important to imagine what the problem is basically asking you, okay? All right, so what else? That it is desired to place a 500 feet column of high strength slurry at the bottom of the casing. The high strength slurry is composed of class, okay, so 500 feet, okay, 500 feet will be basically at the bottom of the casing, right? So you need basically a 500 feet of high strength slurry here, right? Let me use another color here, maybe, I don't know, this color. This is 500 feet of high strength slurry. And what else remains? 2,000 feet more, right? So let me use this color here. So there are two different types of cement that you're using. So this is kind of a complex problem at the beginning that you guys are seeing, but I think you will learn about it. So this is a 500 feet of, sorry, this is 500 feet there, right? This is 500 feet. And this is 2,000 feet. Okay, so that 2,000 feet is also mentioned here. So basically you have 500 feet column of high strength slurry at the bottom of the casing. The high strength slurry is composed of class A cement mixed using 2% calcium chloride. So these are the additives that is added to your cement, and a water cement ratio of 5.2 gallons per sack. So that means that if you mix 1 sack of cement, you have to add 5.2 gallons of water to it. Okay, that's called basically the water cement ratio here, right? And you have an additive which is 2%, and this 2% is by weight. We'll talk about it. Okay, calcium chloride. So that's one cement that you have, and then the upper 2,000 feet of the annulus is to be filled with a low density slurry of class A cement mixed with 16% bentonite. Again, this is the weight percent, and a 5% sodium chloride, and a water cement ratio of 13 gallons per sack. So this is the second cement that you have basically to mix and prepare, add it to your annulus. Okay, 2,000 feet, right? Anybody remember what was the mass of a sack of cement? How many pounds of cement is basically one sack?
Was it 46?
46? No. A little higher, not a little, more than a little higher. 94, right? 94 pounds, one sack of cement was equal to, well, we didn't talk about it a lot, right? But anyway, one sack of cement is 94-pound mass, okay? And so two cements here, right? And also, so there are two cements there, and then also we want to fill the that 40 feet as well, okay? So if you go back here, let me see, I guess it's mentioned there. Go back there, please. All right, so the upper 2,000 feet, 40 feet with float car guide shoe is 500. The 2,000 feet annual is to be filled with the low density slurry, class A cement, blah, blah. The high water cement ratio slurry should not be used, should not be used to cement whole section, be it potential flow zones or when unknown flow zones may be present. So what it means is basically that you wanna fill also that 40 feet, right? What cement do you use for that 40 feet of float shoe, right? So this area also needs to be cemented. And for this area, we're gonna use the one that basically does not have a bentonite, which is basically the first cement, right? So this cement should not be used for the bottom part, which is the 40 feet distance between your float collar and guide shoe, okay? The cement that you're gonna use here is going to be basically the one that have CaCl2 and 2% calcium chloride and class A cement, right? So I gotta use this color, I guess I used for this part. Okay. All right. So this is what we need to find the volume for. Okay. And for this problem, we need to calculate basically what? Based on the problem, you need to calculate the, well, you need to also first consider that your hole size is 17 inches. And also you need to calculate the slurry volume and number of sacks of cement, of course, required if the excess factor in the annulus is 1.75. So what is excess factor? Well, nothing is ideal, right? So when you basically design the volume of the cement, you calculate exactly what is the annulus volume here, right? You might have some formation that you may lose your cement to those formation, right? And since that happens usually in almost any case, depending on the field and based on the field experience, they come up with a number which is called excess factor. And excess factor basically tells you that how much extra cement you need to prepare in addition to the volume of the cement that you calculated. Okay, so in this case, the excess factor is 1.75. It means that once you calculated your volume, multiplied by 1.75, because that's probably how much you will lose, right? 75 basically percent will be lost to some formation, right? So this is something to consider, and it basically depends on the field and the field experience that you basically get from other wellbores in the area. Okay, this case given to us, so basically that's what we need to do. All right, so the hole size is 17 inches as well, right? So that was given to us, and we do have also the outer not all the way to this point, right? Maybe to this point. So you also have the outer diameter of your casing. You also have the inner diameter of your casing. And this shoe joint area, basically the inner diameter of this and outer diameter is usually equal to your casing size. Okay, so you can calculate this volume based on the inner diameter of your casing, right? Okay, so let's do some calculations here. And you have basically given also the specific gravity of your cement, which is also in the book, in the tables, but also you have that one, right? So, which is 3.14, and the specific gravity of bentonite, which is also used in these calculations, is basically 2.65, right? Okay, so let's start by doing the calculation. It's basically a mass balance that we want to do here, right? And first thing that you basically need to calculate is to calculate what is the specific gravity of basically the brine mixture that you are, the salt water that you are mixing, okay? Because if you look at the first cement that you have there, the 500 feet cement, you have 2% calcium chloride and water, right? The second cement that you're using, you have basically 5% sodium chloride and water, right? So this is basically, that means that you have salt water, right? Both of these are kind of salt, right? That you want to mix with your water. And you need to calculate, if you mix this solution of basically calcium chloride or sodium chloride with your water, what would be your specific gravity? Okay, so this is basically the first thing that you want to calculate. Okay, and now the overall procedure that I want to talk about it is basically to calculate a yield for the cement slurry. And the unit of the yield is basically cubic feet per sack of cement. That's the unit of yield. And what it means is that per sack of cement that you mixed, how much slurry will you get in volume? This is called the yield of the cement slurry, right? So what we want to do is to calculate this yield for these two cements and basically use that number to calculate the total volume of the cement that we will have and how much cement basically we would need to have, okay? But before doing that, we would need to do some mass balance calculations. And the first thing that we want to do is related to that NaCl and CaCl2, okay? Now, look at the first cement, okay? The first cement, what do you have here? You have basically 2% calcium chloride, right? And water cement ratio of 5.2 gallons per sack, per sack, right? So let me not call it that. Let me call this, I want to start with NaCl calculations and then I'm going to do the CaCl2. So let's calculate basically how much NaCl, which is for the cement number 2, we need. Or basically what would be the specific gravity of that NaCl solution. That's the first thing you want to do. Okay, you have the specific gravity of your class A cement, you have the specific gravity of your bentonite, but you don't have the specific gravity of that salt water that you have, basically. Okay, that's what we want to calculate. All right, how to calculate that? So we have basically the, I'm going to start with this one. I'll tell you what's the reason, but it's basically 5% sodium chloride, right? So this is 5% by weight NaCl, right? Now, when you calculate, this is very important. When you calculate all these basically masses initially, all of them are based on 1 sack of cement. So you assume that you want to use 1 sack of cement. Now, how much other properties or other basically additives you would need? Okay. What is the reason? Because the yield is per sack of cement, right? and I want to calculate yield. So every calculation is going to be based on 1 sack of cement initially, okay? And 1 sack of cement is 94 pound mass. Any questions so far?
So you would just do the percent of that 94 pounds without the water added?
Exactly. So for NaCl, I have 5% weight, right? So that means that how much NaCl I need, the weight of NaCl is equal to 5%, which is 0.05, right? Multiplied by 94 pound mass, which is 1 sack of cement, right? So that is equal to 0.05 multiplied by 94 is 4.7 pound mass of NaCl, right? Now, how do we calculate the specific gravity for these basically salt mixtures? There are 2 tables in your book in chapter 2. This is table 2.3 and table 2.4. One is for NaCl solutions and one is for CaCl2 solutions. Okay. Now, if you have basically the percent of NaCl by weight in the solution, right? You can just use this table to give you the specific gravity. Kind of made it easier. You can calculate it for sure if you don't have this table too, but this table makes it easier for you. Okay, so percent NaCl by weight in solution. There are some basically weight of solution per gallon, pounds of NaCl added to water per basically cubic feet or barrel. So there are many ways of basically giving you exact basically value, right? But what we want to do is to calculate the mass of NaCl that we need, right? And divide it by total mass of basically the solution. So we have the mass percent per solution. This is 5% NaCl, right? With respect to the amount of cement, right? Don't mix this up with 5% solution. This is not 5% solution, right? This is 5% by weight NaCl with respect to 1 sack of cement. That's what this number is, right? Now I calculated basically how much mass that would be because 1 sack is 94 pound mass. So that's 4.7 pound, right? And how much do I have water? I'm using 5.2 gallons per sack, right? And what does that mean? Is that one? Or no, I'm mistaken. That's calcium chloride, right? I have 13 gallons per sack for the one that is 5% sodium chloride, right? That's how I should mix it, right? So 13 gallons per sack, right? So the weight of the water is equal to 13 gallons per sack, right? And 1 sack of cement is equal to 94 pound mass. Did I do it wrong? I guess I did, right?
Would you convert how many pounds per sack? So would you do gallons to 8.34 to get pound mass per sack, or?
Yeah, I think I did a mistake here. Yeah. Yeah. So I have 13 gallons per sack, right? And that's basically 13 gallons per sack, or can be multiplied by the density of the water, which is pound per gallon, right?
Yeah.
So that would be pound. So what I shouldn't write here is this sack here. Why? because all of my calculations currently are based on 1 sack of cement. Even this one was based on 1 sack, right? So I don't need really to write that, right? It's basically if I want to mix 1 sack of cement, I need 13 gallons of water, right? And how much would that weight is basically multiplying by the density of the water. So that's 13 gallons of water multiplied by 8.34 pound per gallon, right? That's the density of just normal fresh water, right? Is equal to, if you multiply 13 by 8.34, 108.4, right? 108.4 pound mass. So I need 108.4 pound mass for 1 sack of cement. It is per sack of cement. This is also per sack of cement, right? Because these calculations are based on that. Now, I want to calculate the weight fraction of basically this NaCl, and that's pretty simple, right? So the weight fraction is equal to 4.7 divided by 4.7 plus 108.4. This is fresh water, right? This is not salt water. This is fresh water. This is salt. You mix them together, right? You divide 4.7 by 4.7 plus 108, and that gives you 0.0415. That's the weight fraction. Now you go to the table, and how much was that? 0.04, right? And per basically, I'm talking about the NaCl solution, right? So this is percent, right? So this is 4% here. If you look at per solution, right? I'm using this one. Percent NaCl by weight of solution, right? That's exactly what I calculated here, right? And mine is 4.15, right, percent. This is 4, this is 6, right? So I am somewhere in between. I can do interpolations, right? And get basically what value would that be, right? Or I can use just this number, slightly increase, but I did already calculate, I did the interpolation. You know how to do the interpolation, I guess, right? 4, 6%, right? These are these two numbers here, right? And then a specific gravity is on y-axis. This is the percentage, right? For 4, that's going to be 1.02. What happened to my graph? Okay, 1.02. And then for 6%, that's 1 point. For 6% is going to be 1.04. What happens to my graph? 1.06. And then these are 2 points. You connect them together. You want a number at 4.15. You want this number, right? You can find the equation for this linear line and then, find that point. But here is not important at this point. I already did that. So I calculated basically with the interpolation that your specific gravity, you can write it with gamma. Gamma is not for this one. We can just say SG, specific gravity of NaCl, or I shouldn't say NaCl, I can say just salt water here, right? Of salt water is equal to 1.0279, and doesn't have unit, right? The specific gravity is with respect to fresh water, basically, right? So that's my specific gravity for here. I do have the specific gravity of cement, and I do have also the specific gravity of bentonite, right? Okay, so that's for cement number 2 here, right? And for cement number 1, also I have a salt, so let me calculate that also at the same point since we are talking about that. We have a CaCl2 solution. And what is that? In the CaCl2 solution, you have 2% calcium chloride with 5.2 gallons per sack. So that's 2%. So again, weight of CaCl2 is equal to 0.02 multiplied by 94 pound per mass, right? And that is equal to 1.88 pound mass, okay? And then the weight of the water, again, similar method. This time is 5.2. So 5.2 gallons multiplied by 8.34 pound per gallon. So we get how much mass this needs, right? That is going to be 43.4 pound mass. Finally, we calculate the weight fraction. And that is equal to 1.88 pound mass divided by 1.88 plus 43.4. This is the solution. This is just the CaCl2. And if you do the calculation, you get 0.04 that's again 0.0415, right? So exactly same as that one. Coincidence. But if you go here, then there is another table which gives you again percent CaCl2, this time by weight of solution. For you wanna interpolate there, and I already did that. So specific gravity of salt water for cement number 1 is equal to 1.0329. All right, any questions here? How to calculate all these mass percentages, things like that? No question? All right. So we have specific gravities set here for the water salt solution, and what you would need here to do is kind of plot a table for each cement. Okay, so let's start with cement that basically we started with here. That's basically cement that have bentonite. We can start with this one again, right? The upper 2000 feet. This is the first cement that you want to inject, right? Because if you look at here, you first inject this yellow cement, which is that 2000 feet bentonite NaCl mixture, right? Once it reaches there, then you inject the next cement right away after that one, right? So that's why I did the calculation for that one first. And let's continue that basically calculation. I shouldn't call this one 2. I should actually call this one cement number 1, but based on the problem, I guess I named it that way. Anyway, so let's start with that 2000 feet one. So you want to create a table to do your calculations. So component, volume. That's what you want to calculate, the volume, right? Remember, the yield is cubic feet per sack. I want to calculate that cubic feet, right, for each cement. So this is going to be cubic feet. Okay, 1 here. Now you want to write the components here, right? You have cement, right? You have bentonite, and you have the salt water, right? Make sense? All right, so how to calculate the volume? It's pretty simple. All you need to do is divide mass by density, right? What is the equation for volume? Volume is mass divided by density, right? What is the mass? What is the density? All you need is basically these two parameters for all these three components, right? Now you may notice why we did calculate specific gravity, because that helps us to calculate the density of basically that component, right? So mass of 1 sack of cement, again, per sack of cement is 94 pounds, right? Divided by the density of the cement, right? What is the specific gravity of the cement class A? 3.14 given to us. The specific gravity should be multiplied by what number to get the density? Any idea? So the definition of specific gravity was density of that whatever you are calculating divided by density of the water, right? That's the definition of specific gravity. So what you need to put here is the density of the water, but since this is in pound, you want to put the density of the water in pound per cubic feet. So that gives you cubic feet, right? And that is equal to 62.4 pound per cubic feet, right? And that's going to give you 0.4797 cubic feet of cement. Cement powder we are talking about here, right? Now, bentonite, what is the mass of the bentonite? Again, go back to the top part, 16%, right? So that means that the mass of the bentonite you need is 16% of that 94 pounds. That's the mass of your bentonite divided by the volume. Again, you have the specific gravity given to you, 2.65 multiplied by 62.4 pound per cubic feet, which is the density of the water. And that gives you 0.09. Okay, 1. And finally, the salt water. Now that's where you use that salt water calculation, right? So you got 1.0279 for that NaCl solution, right? And the total mass that you have for that solution is basically the sum of the mass of the water and NaCl, which you used it at the denominator of the weight fraction, right? That's the total mass of that salt water solution, right? So 108.4 plus 4.7, 108.4 plus 4.7 divided by specific gravity that we got from the tables, 279 multiplied by again 62.4. And that is equal to 1.7633. So that's all for this cement, right? Now, what would be the total volume is the sum of these three volumes added together. So this is considering an ideal solution, means that no non-ideality will happen, and the sum of these volumes, if you add them together, will result to the summation of all these volumes added together, right? So that's an ideal solution assumption. And this is the yield of that cement. It's equal to 2.334 cubic feet per sack of cement. Make sense? All right. So this is the first cement, right? And what this cement needs to fill in is basically this yellow area, right? So you can now calculate how much volume of that cement is needed, but first you would need to calculate the annular capacity here, right? Which is based on the 17 inches wellbore and outer diameter of your casing, right? So I can calculate my annulus capacity, pi over 4, which is cross-sectional area first, 17 squared minus 13.375, which was the outer diameter of the casing. And you can convert this basically to square feet by saying that 1 basically feet squared is 144 inches squared because this is inches squared here, right? So that gives you what? That gives you 0.6006 square feet, right? And what is the length that you have here for this one is 2000, right? So the volume of the slurry that is needed is equal to 0.6006 square feet, right? Multiplied by 2000 feet of the annulus that I have, right? This is cross-sectional area of the casing multiplied by the length of that part gives you the volume, but also remember we have excess factor, right? That is equal to 1.75. You need to consider it when you calculate your slurry volume. Make sense? And this is equal to 2102 cubic feet, right? So that cubic feet, how many sacks of cement is required? You use your yield, right? So number of sacks that you would need is equal to that volume, 2102 cubic feet, divided by 2.334 cubic feet per sack of cement, because this is how much slurry you produce per sack of cement. How much slurry in total do you need? 2102 cubic feet divided by this number, you get 901 sacks of cement needed for that section. Does it make sense? Any questions here? So you see that we did not really use any specific equation other than volume balance, volume mass density equation, right? And we could find the number of sacks of cement and how much volume of the slurry is needed for that 2000 feet section, right? Okay, so that's, I guess we are also finishing the time here. So we will continue this problem because there is another 2 more sections to fill in, this area and also this area, these colorful parts that we need to calculate, but the process is exactly the same for that part, but we will continue that on Wednesday, okay? Any questions? Anything?
Nope.
Was it straightforward or no?
Yeah.